more. Okay. And to summarize, he is a polymath, a Renaissance man. He has been awarded with the Presidential Early Career Award, the Chauvenet Prize, the Gauss Lectureship. I said Gauss like French. He's also a teacher, an expositor of mathematics and its applications. And in his spare time, he enjoys animation, video production, and Twitter. Today, he's going to talk about opinion dynamics on sheaves.
Thank you very much for that introduction, Eva, and thank you very much for the invitation to be able to speak with you today. I very much look forward to being able to share some research that is a little bit different than some things that you may have seen before. Most of what I do involves a combination of applied algebraic topology, which generates tools to understand systems, mostly based on classical tools of algebraic topology, homological algebra, things like that. In the past, I don't know, 10 to 15 years, I've been really excited about the potential of sheaves and sheaf theory for being able to solve practical problems. And it's these things that I want to talk about today in the context of something that seems completely unrelated, that is opinion dynamics. So let me start off with just a little bit of information about some classic ideas in opinion dynamics. And here's the setup. Let's say that you have a social network of individuals. You model that network as an undirected graph. So think of something like you see on Twitter, right? Where it's undirected. Pardon me, more like Facebook, not like Twitter. Twitter's directed. I can follow you without you following me. Facebook is undirected. When you're friends with someone, it has to be reciprocal. I said Twitter because I spend all my time on Twitter and none of my time on Facebook. Okay, so you've got this network and you assume that everybody has an opinion on some topic. Let's pick one topic that people have opinions on. No, I don't want to pick that topic. That's too controversial. Let's pick something, I don't know, a little simpler. If you saw the advertisement for this talk, I did not have a beard. And now I do have a beard because I'm not teaching undergrads anymore. Some of you might like that. Some of you might not like that. Let's model that opinion as being either no, Rob, shave, get rid of the beard, or yes, I kind of like it. It looks distinguished. You look older, or maybe you just don't care. And what we're going to do is model this as a real valued opinion so that we can encode some intensity of opinion. You could be like kind of positive or really, really positive, or kind of negative or really, really negative. Or if you don't care, then you're at a perfect 0. Okay, now here's the problem. What happens to people's opinions over time, assuming that there's some sort of mutual influence over the social network? So we've got some network. Everybody starts off with an opinion. Maybe you like it, maybe you don't. Over time, what is going to happen? Maybe things evolve into a sort of a polarized state, where there are groups of people who like it, groups of people who don't like it, and some people who just don't care. Or maybe the system comes to a sort of consensus where eventually everybody believes the same thing. What's going to happen? Well, based on your experience with social networks, you may already know the expected answer to this, but there are some classical results that will be the springboard for the research I'm going to talk about today. The one that I think is just really key to understanding is a 1968 paper by Taylor on how opinions spread over networks. And Taylor uses something called the graph Laplacian to predict changes in opinions. Now, the graph Laplacian, this is something you may know. It's something you may not know. Let's recall a little something about the graph Laplacian. This is not difficult. It's pretty ubiquitous. We teach it to our undergrads all the time. Given an undirected graph, the graph Laplacian is a matrix on the size of the vertices, so a square matrix. And what it is along the diagonal, you record the degrees of the vertices, and then on the off diagonals, you use the adjacency matrix with a minus sign in front of it. That's one way to represent the graph Laplacian. The other way is in terms of the boundary matrix. This is BB transpose. I don't know why that transpose looks funny on the screen, but there are a couple of different ways to define the graph Laplacian. It's really, really useful in a lot of different contexts, not just network science and combinatorics. Okay, back to the story. How did Taylor use the graph Laplacian to model opinion dynamics? He set up a diffusion process, basically a heat equation. So let's register everybody's opinion as a vector x that depends on continuous time t. So all the vertices have opinions. This is all bundled up into a big vector x, and dx dt is going to be proportional to the Laplacian of x with some negative constant of proportionality. This is really a heat equation if this were a classical Laplacian. This is a continuous time version. You can do a discrete time version where time increments, and instead of the Laplacian, use the identity minus the Laplacian by discretizing that derivative on the left. In either case, continuous time, discrete time, the theorem is the same. Any initial condition converges exponentially to a consensus state where locally everybody agrees. So if you have a connected social network, eventually everybody comes into agreement. That is a result from 1968, and that ended the subject because that means that, well, everybody always agrees. And in fact, what it says is that the more connections you have in your social network, the faster everybody comes to agreement. How does that measure up with things that we see on Facebook, on Twitter, in everyday life? Not so good. I mean, that's a nice theorem, but that's not really the way the things seem to go. We get polarization. Why? Well, a lot of the work since then has gone on to try to explain that. This is a huge subject and one that is rapidly accelerating, so it's going to be impossible for me to relate everything that's been done. But most of the current work in this area is focused on more complex settings or more complex outcomes than consensus. Some work has focused on multiple opinions, where instead of just one topic that everybody has an opinion about, we have n different topics. And in this case, one can use something called the graph connection Laplacian by Bandara, Singer. Lots of other people have done modifications of this to get similar types of results. In order to explain things like polarization, one thing that many people have turned to are called bounded confidence models. So this is models where that diffusion, that influence, only occurs when the opinions aren't too far away. So if you've got a neighbor who's just a wacko, you're just not going to trust anything they say, and so they don't influence you. Hegselman and Krauss invented one such model. There's lots of other options, lots of alternatives that people have looked at. And there's just so much more. Huge subject. People have looked at preference falsification, antagonistic interactions where people are purposefully rare, kind of like Twitter. Susceptibility, where some people are really open to influence, others not so much. Most of the techniques in this subject involve graph theory. There's some ideas from game theory, differential equations, more. If I look at the subject, try to make some observations, one of the things that I note is that almost all the work in the subject is based in some form or fashion on graph theoretic methods. Not a surprise, since we're talking about social networks. Many of these works have increasingly complex models, trying to build in this new feature, that new feature, and making the models more and more complex as a result. My goal in approaching this subject was to try to cut through some of that complexity and give a broad but simple model that is based on some ideas from algebraic topology and Sheaves. Sheaves, and in particular, sheaf cohomology. And what I want to turn to now is some of the background on those topics. So we're going to diverge from opinions for just a few moments and talk some technical terms about sheaves. What's a sheaf? Well, in the context of today's talk, a sheaf is going to be a type of algebraic data structure that is attached to some base space. The spaces we're going to work with are all going to be graphs or maybe higher dimensional complexes. And those simple situations are going to have data sitting on top of vertices, edges, other cells, data that is especially simple. We're going to hang out in the world of vector spaces and linear transformations. So nothing too complicated, despite some imposing looking definitions or terminology. All right, so here's the fine print. If I have a base space that is a cell complex, X, let's say a simplicial complex, then a cellular sheaf that is valued in the category of vector spaces and linear transformations assigns to every simplex, every vertex, every edge, every face, everything, a vector space. They're not the same vector space necessarily. They could be very, very different. In the same way that all the cells are glued together, the data, the stuff that's sitting over top of the vector space are glued together via linear transformations. So the intuition is that this stuff, this data that sits over top of the vertices, edges, faces, these are called stalks. And the maps that glue these stalks together are something like compatibility constraints. They're things that you can program. And I very much like the idea of a sheaf as a programmable data structure. Now, what do you do with this? What are some examples? We'll get to the examples later. The one other tool that we really need to talk about is what makes sheaf theory so great, and that is cohomology. In the same way that space has algebraic topological invariance, so does a sheaf. What we can do is take all the data over these cells, all those stalks, we can bundle them together using, let's say, a direct sum, so that we have all the data over the vertices, call that C0. All the data over the edges, call that C1, C2, C3. These are all just big vector spaces. And then one defines a coboundary map in the usual way using those linear transformations that are used to program the sheaf. With that cochain complex, you can use kernel's mod images in order to compress it out into a sequence of quotient vector spaces. This is called the cohomology of the cochain complex, the cohomology of the sheaf. And it records topological features, not just of the space downstairs, but on the data that sits above it. And in particular, the zero-dimensional cohomology, H0. This records what are called the global sections of the sheaf. That is, choices of the data that are consistent with respect to the constraints. So that dimension of H upper 0 is really the number of independent, consistent solutions to the constrained system. And higher dimensional sheaf cohomology is classifying things like obstructions to solutions to various problems. Now, this is all kind of whoa and a little bit out there if you have not become friends with cohomology or sheaves, but let's keep it very simple, very concrete. Everything that I do for the rest of this talk is going to be over a network, over a one-dimensional base space. So the only thing that we have to worry about is the vector spaces over the vertices, the vector spaces over the edges, and linear transformations that go from vertex data to edge data. That's it. It's just a big system of linear transformations. But I'm going to think of this as a data structure over the graph. Okay, now let's get to an example or two. And this is going to be a little weird, but stick with me here. Let's take a very simple discrete time linear system, a recurrence relation, such as we teach our undergraduate students, something in the form xt plus 1 equals some matrix AT times xt. So that's a simple linear system. I can model this in terms of a network sheaf where all the stocks are some fixed vector space where xt lives, and the base space is going to be a graph that is just a discretized timeline. So I've got my timeline discretized according to time step. And what I'm going to do is put the same vector space over each vertex, over each edge, and I'm going to program the sheaf with alternating identity maps and these matrices A sub t that affect the dynamics. And then writing down the condition to be a cohomology class, an H upper 0, what that really gives me is the equation xt plus 1 equals at xt, right? I start with xt right here in the middle and map it to the right by at, and then I have xt plus 1 over to the right, and I map it to the left by the identity map. These have to match up in order to be a global section. So that H upper 0 classifies global time solutions. Now, you might know something about recurrence relations, discrete time dynamical systems, and you might say, well, couldn't we do something more complicated? What about your basic linear control system where you have observables and user inputs and all these sorts of things? And maybe you've seen these systems before, maybe not. If you have seen them, then one can build solutions to these equations as the cohomology of a network sheaf. We just have to make the network a little bit more complicated to account for these user inputs, U sub t, and these outputs, Y sub t. And then we have to program the sheaf with the appropriate sequence of projection maps, identity maps, these matrices, A, B, C, D, all that kind of stuff. So if you have in your mind the image of being able to build really complex networks of algebraic constraints and using sheaf cohomology to classify solutions to those systems, that's the right way to think about it. Now, these sheaves, these network sheaves, have recently been useful in a whole bunch of different settings, and several people from my research group have been really interested in developing some of this technology. But there's one more tool that we need to talk about that really makes all of these applications happen. And this is the Laplacian. Remember, when we were talking about opinion dynamics, how important the Laplacian was. Well, it's going to be important again to us for the rest of this talk. What I'm going to discuss now is joint work with my former PhD student, Jakob Hansen, who's now a postdoc at Ohio State, really excellent guy. And the two of us together have been doing a lot with sheaf Laplacians. The idea is this: we're going to extend the graph Laplacian to a Laplacian on sheaves. If I take that sequence of algebraic data from the sheaf, where I look at all the data over all the vertices, all the data over all the edges, and in a higher dimensional setting, higher dimensional data as well. Then, if these sheaves are valued not just in vector spaces, but in inner product spaces, so that I have some sort of notion of geometry, then we can take the adjoint of the coboundary map. And instead of going up in degree, we can also go down in degree. That adjoint allows us to define a classic Laplacian that in algebraic geometry would be called the Hodge Laplacian. And this gives an automorphism on cochains, a degree preserving automorphism. So it takes data over vertices to data over vertices. It takes data over edges to data over edges. And this Laplacian is very cool, very useful, and is a natural generalization of the graph Laplacian. Now, why is that? Well, let's say we have the simplest possible case where my space X is just a graph and the sheaf over top of it has one-dimensional vector spaces with identity maps everywhere. This is called the constant sheaf. The Hodge Laplacian, the sheaf Laplacian of that constant sheaf, is nothing more than the graph Laplacian. But we can make this work for higher dimensional complexes too. We can do so much more with it. Here's a nice, if easy, theorem. This is the analog of the Hodge theorem. The kernel of the sheaf Laplacian computes the cohomology of the sheaf. Things in the kernel of the Laplacian are, of course, called harmonic cochains. These harmonic cochains are isomorphic to the sheaf cohomology. And lastly, in grading 0, I can use the Laplacian on vertex data to define a quadratic form that tells you how far away you are from being a cohomology class, from being a global section. All of these results here have analogs in graph theory based on things like the number of 0 eigenvalues of the graph Laplacian, things like that. There's actually a really rich theory of spectral sheaf theory that is a lifting of spectral graph theory. We're not going to get into that today because what we're going to focus on is opinion dynamics. And I want to talk about a sheaf that models opinion dynamics. These are called discourse sheaves. And if you found the previous material that we went over to be a little obtuse, complicated, then time to exhale a little bit, because this is going to be not so bad. Let's consider a social network, and let's consider the following sheaf of vector spaces. What we're going to do is we're going to say that the vector spaces over the vertices are opinion spaces. These are going to be vector spaces that have an explicit basis of things that you really care about, things that you have a basis opinion on. So I've got my basis opinions, my opinion space, the things that I care about, but you've got your basis opinions and your opinion space. They're not necessarily the same opinions at all. These vector spaces are not necessarily the same dimension. Now, when the two of us get together and talk, what we set up is a discourse space over the edge between us. There are some topics that we're going to express opinions on. They are not necessarily everything that we have opinions on. No, 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 no. There's some subset or some collection of things that will be used as a basis for opinions to be discussed. And these sheaf maps, these maps that go from the vertex data to the edge data, are presumed to be linear transformations that are expressions of opinion, formulations of opinions from your basis beliefs. And then this continues for every possible edge in the social network. Let me give a somewhat ridiculous sort of example. Let's say that there's just the two of us, you and me, and we're talking about one topic and only one topic. And that topic is, shall we walk to town and get some tapas? What do you think about that? I know what I think about that. What do you think about that? Well, maybe what you really care about is how much you like to walk and whether or not you're hungry. Those are the things that are really going to influence your belief. And maybe you're kind of hungry, but maybe you're really not in the mood to walk. You're tired. You don't want to walk to get some tapas. Me, on the other hand, what do I care about? I'll tell you what I care about. This. right here. This is some delicious jamon, jamón ibérico de bellota. So I really care about that. And the other thing that is a basis opinion for me is this right here, the vino tinto, very nice bottle of Muja. Okay, so those are my basis opinions, and I'm right here in this opinion space. I'm like, man, I could really go for some jamon. So I'm going to express my opinion based on that, and we disagree. We disagree, but that's cool. I think if we came to consensus, we would vote to go out and get some tapas, and then everyone would be moderately happy. Okay, now that's a silly example, but it illustrates how flexible this model is. It allows for people to have many different opinions about lots of different things, to keep them private, to talk about things that are not necessarily just blankly sharing exactly what you feel. These mappings are linear transformations. That means that they can have negative coefficients as well as positive coefficients. I can, if you will, lie about a topic. And I can do so selectively. I can lie to you, but not to you. I could say different things to different people, even if they're talking about the same topic. And that's what's so cool about a sheaf of vector spaces, is you can have this strong heterogeneity and you can program the sheaf to accommodate that. And in the context of this example, all of this complicated stuff with zero cochains and one cochains and co-boundary maps, Laplacians and global sections, all that blah, 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 it all has very, very concrete interpretations, right? Zero cochains are private opinion distributions on your basis opinions. One cochains are public pairwise discussions. The co-boundary is telling you something about the aggregate disagreement in things that people are talking about. The Laplacian is telling you about how far your opinions deviate from sort of an average consensus opinion in terms of what's being expressed. And most importantly, because the kernel of the Laplacian really gives you the sheaf cohomology, then those global sections, that H upper zero, consists of literally harmonic opinion distributions, distributions of opinions that lead to expressed agreement or expressed consensus over all the topics that are being discussed. That's actually kind of deep. It's a very cool interpretation for this model. And that leads us to the topic of harmonic opinion distributions and convergence thereunto. The principal theorem that gets things started, not the hardest theorem I'm going to talk about, but the big one that gets it all going, is the following. If we use this sheaf Laplacian to set up a heat equation on a discourse sheaf, on cochains of opinion distributions. If I write down this heat equation, dx dt equals minus alpha, some positive constant, times the Laplacian of x. This is on zero cochains. Or if I do the discrete time version, then every initial zero cochain, every initial opinion distribution converges exponentially to the closest harmonic distribution. This is the sheaf analog of Taylor's theorem. And it means that there will be consensus in the form of expressed opinions. Now, what I mean by closest is via orthogonal projection to the space of global sections, which can be interpreted as a zero cochain. The proof of this is not hard. It's based on the fact that the sheaf Laplacian is positive semi-definite. You analyze the eigenvalues. This is not a difficult result. What is, I think, more difficult is, what does it mean? Does this mean, like in Taylor's theory, that everybody agrees? No, not necessarily. You still have your own basis opinions, and things have been modified slightly so that there's an expression of agreement about the topics that we're talking about. Okay, well, that's kind of That's kind of cool. But as I said, that's just getting things started. What comes next? Well, let's use this language of harmonic opinion distributions to push things forward. What happens if we have people who are stubborn, who will not change their opinion no matter what you say to them? I'm not sure that I've ever met anybody like that, but maybe you've met somebody like that. Who knows? How do we account for people who are not influenced by others? The way that we're going to do it is through the idea of a harmonic extension. If we modify that heat equation based on some subset U of stubborn people who will not change, so that we have that heat equation off of U, but on U, the dynamics are null. These people just don't change at all. Then what happens in this case? What happens in this case is every initial condition converges exponentially to the closest harmonic extension of the initial opinion distribution on this set of stubborn agents. So this language that we're used to from harmonic analysis that works perfectly in this sheaf theoretic context. Now, since you're probably wondering, yes, such a harmonic extension always exists, and it is unique if a certain relative cohomology class vanishes. And that vanishing, that obstruction, is really key to being able to understand how a set of stubborn individuals can influence everybody else. In fact, if you think about it that way, I wonder if instead of just having people who are stubborn, what if we actually control those stubborn people? What if we try to plant propaganda inside of a social network? To what extent can we influence what is going to happen over the network? As you might understand, that is a sadly relevant question in these days. Well, recall the example we did before, where we did a standard time-dependent linear control system in terms of programming a sheaf. Can we do the same sort of thing here? Yes. I'm going to skip some details for the sake of time, but the rough idea is the following. If we have some harmonic distribution, something that is the net result of the evolution of a heat equation, in this restricted dynamic setting where we set up observables, controllables, all that kind of stuff, let's say that we have some subset U of agents that we can control. These are like the user inputs in a classical control theory problem. And then we have some other subsets of people who are observables. These are like the user outputs instead of the user inputs. These are the observables in a linear control system. Then what can we use to characterize influence of opinions? It's all about sheaf cohomology. The relative H upper 0 of the sheaf with the entire graph X relative to U is the obstruction to controllability of the system, to being able to get the rest of the system to do what you want. And the dual relative cohomology of X rel Y is the obstruction to observability, to being able to infer the state of the rest of the network based on what you're seeing from these observables Y. And now this sounds kind of scary. Maybe it is kind of scary. I think it's less scary than it sounds. These results really require knowing a lot about the entire system, about all of those linear transformations. That's maybe not so easy to engineer in practice, thankfully. However, with things that you and I see maybe on social media, there's certainly a lot of people out there trying to engineer such manipulations of opinions. And I think it better for mathematicians to engage with the subject and find out what can and cannot be done rather than to disengage from the subject and let others experiment. Okay, well, let's get away from creepy things. Let's talk about things that are more fun. Let's talk about learning how to Learning how to communicate better. That sounds positive, right? Yes. Now, everything that I've talked about, this whole model, I don't know. I'm not so sure that it's actually a very accurate model. It's a cool model, don't get me wrong, but I'm not sure how accurate it is. Is it realistic to posit that people are really changing their opinions based on interactions with others? To what extent is that true or not? Well, I'm not a sociologist. I can't answer that question. But I can draw cartoons. So let me draw this cartoon again about the vino and the jamon and the tapas. Do you think it's the case that if we evolve this model by heat equation, that you become more hungry and more likely to walk? I don't know, maybe if we discuss, maybe you decide, yeah, that jamon sounds pretty good. I am kind of hungry, actually, yeah. But what about me? Do I not like jamon so much? Do I not like vino tinto as much because we're talking about it and you're a little more reluctant? I don't think so. I don't think so. But how is it that we can come to consensus without me necessarily changing some very strongly held beliefs that I have? Well, we learn how to communicate better. And what that means mathematically is that instead of setting up a heat equation on the opinion spaces, maybe what we should do is set up the dynamics on the space of discourse sheaves, so that what is changing over time is not the opinions, or maybe even not just the opinions, but the actual structure of the sheaf. Here is what I think is the most important theorem of the talk. If we take an initial opinion distribution on a discourse sheaf, and instead of flowing the opinions, if we flow the maps that glue the vertex data to the edge data, if we evolve the maps that express our opinions according to what is basically a sheaf Laplacian, it doesn't look like it from the way that I've written it, but that's basically what's happening. Then the sheaf will converge to the closest discourse sheaf that has my initial opinion distribution as a global section. And by closest, I mean closest in terms of squared Frobenius norm, et cetera, et cetera. You can look up details in the paper. This is really cool. This means that you can set up this sort of heat equation, these sheaf Laplacian dynamics that model how we change the way we communicate. And of course, you can have a mixed model where both opinions and expressions are changing as well. What does this mean? Well, let's do a cartoon and let's go where you want to go, because I know you want to go here. Let's say that we have a really simple discourse sheaf. Everybody's got a one-dimensional stock. Everybody's thinking about the same thing. Is this person a wise ruler or are they a moron? I'm not going to say who that person is. Maybe I'm just not going to say, but let's say we got some person in mind and everyone's thinking about the same person and everyone just shares their opinion naturally. It's a constant sheaf. Well, if we do that, then we may start off with a lot of polarization, a lot of disparity in opinions. Some people think they're a wise ruler. Some people think that this guy's a moron. But what happens as you communicate and you're communicating and you're communicating? It might not be the case that you're changing your opinion. What might be the case is that you're evolving your expression of opinion. And because of the flexibility of the sheaf model, the person in the middle here who was kind of, yeah, but also, yeah, not a real strong opinion, they've learned how to lie to their neighbor selectively in order that everybody can get along. I like very much the fact that this model allows for that kind of evolution in communication. I think that's a lot more realistic than the setting where people's opinions change. And I thought that this guy was really great, and now I think he's a moron. Or I thought this guy was a real loser, and now I think he's really great. Maybe not so much. Okay, well, really, there is so much more that we could talk about with respect to opinion dynamics, with respect to these models. We're really just at the beginning of the work that we're doing on this. I've been doing a little bit more research into propaganda over social networks. It's very depressing. The only thing that makes it worthwhile is getting to play with Sheaves. And really, this work began as a way to explain sheaves of vector spaces over networks in a way that people could sort of get it and understand why you would care about that sort of structure. But there's really a whole lot more that could be done, that should be done to make sense of sheaves and sheaf cohomology over networks and higher dimensional cell complexes. I think maybe the most important direction that this research should go mathematically is to think beyond sheaves of vector spaces to much more complex algebraic data. What I'd like to very, very briefly just fly through is some new results with my PhD student, Hans Ries, where what we're looking at is not sheaves of vector spaces and linear transformations, but sheaves of lattices, by which I mean algebraic lattices. These are sets outfitted with joins and meets, these algebraic operations that generalize min and max. These are very, very rich algebraic structures. The sheaves and the sheaf maps that go between vertex data and edge data, really interesting subject. Now, it's a long story. I'm going to make it real short. The short version is there's no real good way to do sheaf cohomology other than to talk about global sections, because the category of algebraic lattices and lattice morphisms is not an abelian category. You can't talk about kernels. It's not so easy to work with. But what we can do is define a sheaf Laplacian. This looks scary, but it's really just all defined in terms of meets, that one operation within an algebraic lattice. And it really is a Laplacian, even though it doesn't look like the graph Laplacian. It really is a Laplacian. You can factor this operator in terms of an expansion step where you're pushing a vertex state out to your neighbors, and then a mixing step where you're taking like an intersection or a meet with your neighbor states and then pulling it back to you. That's exactly what a Laplacian does. Now, with this operator, we can prove something that's like a sheaf theoretic version of the Tarski fixed point theorem. Here's the result. If you have a sheaf of complete lattices on a graph, then the global sections of that sheaf can be computed via this sheaf Laplacian, this Tarski Laplacian. This space of global sections, the zero-dimensional cohomology, is really the fixed point set of the identity operator meted with the Tarski Laplacian. And so what you could do is you could just iterate that operator over and over and over again, and the system will converge to a global section. This is fantastic because these are all local operations. It doesn't require any global understanding. And you can actually do a lot of local or distributed logic this way over a network. And this is all really the same thing that we've seen before. If you look at the discrete time version of the heat equation that we were using with opinion dynamics, it's the same operator. But instead of identity minus L, we have the identity meet L. And the fixed point set of that are the harmonic zero cochains. And there's some nice corollaries from this. You get that the global sections are really a non-empty, complete quasi-sublattice, blah, blah, blah. We can actually do this in higher dimensions to define a sort of a putative higher dimensional sheaf cohomology, even though that kind of thing really shouldn't exist for categorical obstructions. There's lots of cool mathematics that one could do with these things, and we're not done with lattices. We're moving on to other more interesting categories as well. There's an incredible amount of mathematics that one could do with this, but also an incredible amount on the applications side. If you think in terms of what you can do with things like convolutional neural networks and machine learning, taking values in categories other than vector spaces, where so many times it's really artificial vectorizing data in machine learning. Working with data in the form in which it's most natural really requires some advanced ideas from mathematics, but that is why we mathematicians are here in order to be able to do that. Okay, I'm going to stop there. I'm going to thank you very much for your attention. I'm going to thank all the people who are currently or have recently been in my research group. And I very much want to thank the US Department of Defense for funding the work that I do. Thank you very much.
Thanks a lot for this wonderful talk. And Ifeto is here, ready to, in the right moment. So now it's time for questions. You can just unmute yourself and ask the question, or if you are very shy, you can put it on the chat, whatever. Questions?
Question?
Yeah.
Yeah. Hi, I am Martin. I'm with a nickname there.
We don't see you, Martin. We saw you before. Okay, now we see you. Yeah.
Now you can see me. Hi. Yes. So it's an observation that your work, I mean, that goes without saying probably, and it was a fantastic talk, really inspired. I really thank you. It's a question about the linearity of the model, the fact that you're considering linear maps on all these simplexes, on all these edges indeed. I wonder, I mean, if this, at least at the level of the formalism, you can allow like more general functions like polynomial, piecewise linear, or continuous. And if this is something that can be, I don't know, transmitted through all this formalism and maybe be useful in applications where, for instance, in neural networks, you probably need more like piecewise linear.
Yeah, that's a fantastic question. And you're absolutely right. It would be very, very useful to allow for nonlinear maps inside of these sheaves. I know how to put nonlinearity into the dynamics or how things evolve, right? All of the heat equation stuff that I wrote down, those are all linear equations. We can make those equations nonlinear, and there's a lot of work in the opinion dynamics literature that uses nonlinear models to great effect. We haven't done much with that yet, just a little bit, but there's a lot more that one could do there. Where I get stuck is trying to put nonlinear maps into the sheaf, because to be a sheaf, it really has to be a functor from the face post set in order to some category of data. And that category of data has morphisms, and I don't know how to get nice nonlinear morphisms for vector spaces or much else. So I'm not saying that it's impossible. This room is full of all kinds of smart people who can figure all kinds of great things out, but I don't know how to do it.
Can I ask a question? Thank you. So Robert, thank you very much for the talk. My name is Leo. I'm from the Network Science Institute at Northeastern University. And I think this is really, really, really interesting. And I really wish it like sort of catches on in the network science community. My question is, I think, sort of piggybacking on the previous question is, I was surprised to hear about moving on to the lattice category. I'm wondering what is the motivation behind this, especially since, like you said, it's not an abelian category. I was expecting you to mention Hilbert spaces, for example, in which case you could also have like linear transformations, like answering the previous question. So why lattices?
That's a great question, Leo. My motivation for using lattices is logic. I want to solve problems in distributed logic. I want to be able to put much richer data over top of vertices. So this idea of an opinion just being an intensity of like or don't like is very primitive. It's a good start, but I think that the way people build opinions based on chains of evidence, based on things that they've heard, I think that that's a much more discrete and complex structure than just a vector space. And I think that lattices offer the sort of broadest possible class of structures for which one can still prove theorems. It's sort of right at the boundary of what I think can be done.
That makes sense. I guess kind of like now I'm picturing sort of each node has sort of a graph assigned to it, right? I mean, a lattice is basically a graph. So I guess is that kind of what you're trying to go for?
Yeah, you could think about it that way. There's lots of different ways to visualize lattices, but yeah.
That makes sense. Thank you very much.
Mm-hmm.
Okay, thank you very much, Leo, for your question. Now we have a question from somebody that is following you in Twitter, from Bit2Check. I don't know if Bit, do you want to talk or you want me to ask the question? Bit, you're around? Okay, well, he's asking like two questions. The first one is one that I also wanted to ask, so I'm gonna go for it. Did you perform some experiments that would confirm or disprove the dynamics that you described? For instance, this is something I'm adding, no? This interesting, your microphone, the microphone is broken, so he apologizes for not asking you directly. But for instance, this interesting idea that you gave us of that changing the opinion lies in H0, it's fantastic. You can program it. Now I have a PhD student here, Paul, who could do a program to compute this. And so this is like, this is quite surprising. I mean, do you have some experiments that could confirm these results?
Yeah, so the answer to that question is nope, none, not at all. This is very recent work.
Yeah, but this would be interesting to show to somebody in sociology, just ask them to do this. Ask them to catch some data. You do the program you try to put an opinion about, well, you don't want to be controversial, so you don't choose a controversial topic, and then you go for it. This would be amazing, right?
Yeah, it's pretty well outside of my domain of expertise to be able to conduct such experiments. So I would welcome someone who's interested in doing it, but I myself have not done so.
Okay.
There's another question there, if I can read it. This is about considering an extension to higher dimensional cell complexes, where the higher dimensional simplices correspond to communities or groups of people in mutual discussion. And that's really interesting because, if we had three people talking about something, it might be very different if we're all talking pairwise versus if we're all out and talking at the same time.
Yeah.
I think that there's probably some interesting differences there, but I also think that those sorts of dynamics are going to require breaking the sheaf condition a little bit, because if you know what is happening on the vertices, then the sheaf condition, the functoriality, means that everything just chains up in dimension and everything's done, right? The global sections are determined by the one skeleton. You don't need any higher dimensional cells. So there's some work to be done there, for sure.
Ask a question. It's a meta question. What I'm trying to understand is when and how did you make the jump from thinking that sheaves could be a nice way to model this? So we have, you have spoken quite a bit nicely about the model, and I'm just wondering, so as you said, there was just this one research by Taylor, and then you sort of thought, okay, I mean, we find this in many other sciences, right? Let's say, I don't know, air transport or transportation systems or some sort of system, right? And it's like, how do you decide, okay, I think sheaves could fit this perfectly? Because, you know, it is quite general. Topological spaces are so general, you can kind of model a lot of things. So how is that process like, or was in this case?
Well, that's an interesting question. I think most mathematicians will admit that the way they tell the story in the paper or in the talk is usually much different than the natural evolution of a work. Maybe that's true for other people here, maybe not. For me, I believe I said at one point in the talk that really I started working on these models not to solve any particular problems in opinion dynamics, but rather to find a good set of examples of sheaves that I could explain to people and explain why they were useful or relevant. The flexibility that you have in being able to program the maps along all the different edges of the sheaf, the ability to get people to, sort of flip their expressions of what they believe. I think that it's much easier to see or to understand those aspects of a cellular sheaf when you're interpreting it in the context of opinion dynamics, just because that's such a natural part of where we live, where we discuss with people, talking about politics, talking about things online, anything like that. We sort of live in that space a lot. And so it's a little bit easier to see how a model would apply there. I could take this exact same model and rewrite everything in the context of, fairly, forgive me, please, fairly boring economics and try to get some game theoretic results, things like that. And I don't know that people would care so much. I don't know. Maybe some people would. I could write this as just a purely abstract, there's no interpretation, here's the theorem. And then I think really nobody would care. I don't know. I mean, I'm in dangerous waters here. I'm going to get attacked. But there's so much about mathematics that is dependent on its interpretations and on the context in which you frame it. And I think that we mathematicians need to do a better job of framing what we do in a way that people who aren't mathematicians can say, oh yeah, I could see why that's interesting, even though I don't understand all the details.
And also so that such people don't, like, halfway through the process, they might realize maybe they made some really wrong assumptions, for example, right? That might come more natural. I mean, because it's mathematics, so you don't make bad assumptions. But okay, thanks a lot.
Yeah, thank you.
Thank you. We have more questions here on the chat. Carlos Casacuberta, do you want to speak?
Oh, thank you. No, I was just curious about the possibilities of these techniques to ease consensus. So because you always assume a fixed size of your network, but imagine that you want to add, let's say, mediators. You want to add additional vertices with a task to interact in order to facilitate the consensus. Did you ever consider this?
Yeah, so one of the things that I like about what you can do with sheaves, with sheaf theory, is that they themselves have morphisms. You can talk about morphisms between two sheaves. If a sheaf is just a functor between the face post set and a data category, then you could take two sheaves and look at a natural transformation, and then that's a morphism between them. And what that means is that you could talk about what is happening in a sequence of such sheaves over time. And that can involve changing the number of agents. That can involve changing a lot of the structure. You need some notion of relationship between incident time steps that's programmed into the sheaf morphism, into that natural transformation. But it's such a flexible language for being able to describe really complex evolving systems. Yeah, I mean, all the operations that are common to sheaf theory, things like taking tensor products, things like various pullbacks, push forwards, all these things. Yeah, what does that mean in the context of these particular sheaves? You know, I don't know that I've thought about that very much, but there is no end of structure available for exploitation.
Thank you. Are you happy, Carlos, with this? Okay.
Yes, yes, yes. It's a world of possibilities.
Exactly. It's a world, like, I don't know, QNet formula, whatever. You have to find the interpretation. So we have a very interesting question from Sharal. Sharal also found you on Twitter. He's an engineer and he's a bit shy to ask. So I'm going to ask, I think it's a very good question. Do you have any suggestions for somebody with an engineering background in order to get started, understand and contribute maybe to this topic? Because it's really interesting and also terrifying for somebody outside the world of sheaves.
Yeah, so let me start off by saying that my background is in engineering. My undergraduate degree is in engineering, and I'm sort of half mathematician and half engineer now. So I'm with you there. And if I had shown this to me of 20 years ago, I would have found it terrifying as well. One of the things that I found working with engineers is that they are absolutely fearless about learning new things once they have the motivation to do so. Once they see that they need a tool in order to be able to solve a problem, then they can learn anything, no problem. And there's nothing in the tools that I've talked about that is fundamentally difficult to learn. It is, from a language point of view, intimidating and a little bit challenging. But again, having a good set of sort of grounded examples that you're motivated to wrap your head around, that's helpful. I don't have as much for you in terms of practical things. So here's the Ultimate Engineer's Guide to Working with Sheaves. My student, Jakob Hansen, has written up some notes that he has on his website that are for people who would like to get a little bit of background in that. I don't have a copy of those locally, but let me look up while I'm talking. I'll try to look this up and see if I can find them. He needs to update his website. Okay. So why don't we have someone else ask me a question while I look this up, and
Yes.
I will try to put a link in the chat.
Okay. Okay, thanks, Sharal, for asking this question. And now there is Jaume who wants to ask a question.
Hello, I'm Jaume Amorós from Polytechnica. And the question is, nowadays in algebraic topology, there is a fashion for computing homology and cohomology in characteristic 2. So the question is whether there is a Laplacian for vector spaces in characteristic 2.
Oh.
So off the top of my head, I can't say for sure. The entire problem is in the construction of an adjoint. So do you have sufficient weights to be able to get an adjoint? But I think in characteristic 2, it's easier, not harder, to come up with an adjoint.
Well, you have non-degenerate bilinear forms. That much is true.
I'm gonna flip a coin and say, yeah, I think so, but I don't know. I don't really know. But the entire problem is how do you compute adjoints? It's really easy to do if you've got real vector spaces or complex vector spaces, but other characteristics, haven't thought about it. Good question.
Okay, thank you.
Good. Robert just left the web page of his student, so you can find the notes there, right?
That's right. There's something called a gentle introduction to sheaves on graphs. And it's got a few exercises in it and a little bit of background on the homological algebra and some applications.
Very good, thank you. So now we have Irene Ferri. Irene, do you want to go ahead and ask yourself? Unmute yourself and talk. I don't see you, Irene.
Yes, hello. Okay. Yeah, very nice talk. It's really, really interesting. My question is about if there's any way to incorporate new ideas into the flow of information of the network so that social change throughout time can be described as well with this model.
Oh, that's a great question. And it falls under that category of there's so many things on the list of things that can be done to play around with this model. For what you say specifically, where I would start with is looking at a sort of a system that has some stubborn agents in it, let's say, but instead of keeping their opinions fixed over time, what they're doing is they're changing over time, but you're controlling them.
Yeah.
So some of the theorems that I talked about said that if you control some user inputs with a fixed opinion, then you can drive the rest of the system to its harmonic extension. But what if you, let's say, drove it with a periodic input? Then what could you drive the rest of the system to? That's a really cool question. Never thought about it. I have no idea.
Thank you. So useful answer. Thank you.
Okay, great. Any other questions? You can raise your hand or put it on the chat. Yes, Luis has a question. Go ahead. Luis, I'm going to ask you to unmute yourself.
Yes, sorry. I am not very quick in unmuting. I have a stupid question, but it's a motivatory one. While you were talking, I am from applied mathematics, and I'm not a topologist. So, but I am very interested in when you said. By the way, I want to tell you that I like very much your talk because I like the subjects where there is a mix of many things from different fields. I think that this is very rich, and those are theories that they are very powerful and very strong, and I like this very much. Okay, but while you were talking, I could not avoid thinking in the perspective of a physicist or a mathematician in the world of complex systems, where they use some statistical tools, some combinatoric basic graph theory to attack similar problems. Okay, my question is, what is the difference between the techniques you are introducing and those basic techniques? I presume that you will be saying that with what you are doing, you see better the structure of the network, better the evolution of the network. But okay, this is my question, and it could be motivation to attack those problems from this topological point of view.
Okay, thank you. That's a great question, and I'll give an incomplete answer because a complete answer would require going through an entire huge literature that has lots of great work in it. But the things that are distinctive about the approach that we've taken is that there's one model, this idea of a discourse sheaf, that simultaneously captures the individual features of dozens of different models that were sort of custom built to allow people to exaggerate, or custom built to allow people to falsify their preference, or any of a number of other things. There's one simple model that covers everything. Because of the language of Laplacians and harmonic distributions, we can import intuition from the subject, from things like, oh, well, let's just take a harmonic extension. that if you translate this into the more classical literature, which you could do, you could erase all the Sheaves stuff and just talk about lots and lots of linear transformations, you would be missing that unifying principle, and your proofs would be much, much more complicated. And indeed, all the proofs in the paper that this work is based on, they're really short and they're really clean because of the perspective. But I think the last and the most distinctive feature of this work, the thing that I really hope crosses over into the applied math world more, is cohomology. Cohomology is just absolutely an amazing tool in mathematics. And time again, in different contexts in applied mathematics, people have sort of accidentally discovered a cohomology group as an obstruction to solving some problem, but they didn't realize it as such. When you know the theory in advance, when you can see, oh, what's the obstruction to this problem? Oh, it's this cohomology group. It's this cohomology group for this problem. It's this cohomology group from this problem. That is a superpower. And I would love to see that perspective cross over more fully into applied mathematics.
Thank you very much. You clarified very well what I needed to know. Okay, thank you.
Thank you.
Thank you, Luis. We have more questions. You are very successful. We have Moik who wants to ask you again. Moik, go on.
So I very quickly about this intuitionistic logic elements in Sheaves. Recently, I was evaluating this, or I was in a situation, engineering stuff, and I thought, classical logic doesn't really fit here. This is really not a yes or no question. Can I do something different? And at that time, I was reading quite a bit about Sheaves, and then, we found out about the intuitionistic school of logic. Do you think if we come across such elements, let's call them in this case, intuitionistic logic specifically, if these could be entry points for, well, let's say engineers to see, okay, this is probably a situation which does require a bit of modeling, and logically it seems to make, sense in a different school of logic. Would you say those hints and intuition are enough for one to really pursue like this path, if we can call it, or this theory specifically?
So I'm not really sure how to answer that, in part because that's a pretty general question, but mostly because I'm not a logician. I'm interested in applications of some of the things I've talked about today to logical systems, but I can't claim to have any particular expertise in intuitionist logic or multi-valued logic that would really allow me to say anything authoritative on that question.
Yeah, because it was I don't know, I think one of the books by Saunders MacLean, it just says, see how cool this is that Sheaves can model this, and I just kept getting, I don't know, it was a bit exciting from that perspective, that yes, maybe this opens another door to this. But yeah, as you said, maybe that's a very, very general observation. Yeah,
I think there's reason for excitement, but there's reason for excitement in logic from so many different fronts nowadays in mathematics, not just Sheaves and topoi, but homotopy type theory is one of the coolest things happening in mathematics right now. And there's so much interaction there between logic, type theory, homotopy theory. The universe is a big and wonderful place.
Good, perfect. Any more questions or comments? Indeed, I have a question. Well, Elisenda has a question before I post my question. Elisenda, go ahead. You wanna talk? Elisenda Ortiz? Or you have a problem with the microphone? Can you talk? Okay, Elisenda, I don't see her. Okay. Elisenda is asking, can you tell us this framework exactly about the stability over time of polarized states? She says, I'm pretty much wondering up to which extent we can use the model to thoroughly characterize segregation of opinion. And she says, amazing talk. Love the flexibility and potential of the model. Very inspiring.
Okay, thank you, Alessandra. So this is probably the biggest open problem in the subject is polarization, because diffusion dynamics implies convergence and consensus, but real life experience implies polarization and chaos and all-out war between factions. So how do we make sense of that? And I think that most of the work that I see out there in opinion dynamics is pointed towards solving this problem of how do you explain polarization? How do you get an understanding of that? One of the things that Jakob and I showed towards the end of the paper that this talk is based on is that we can reproduce the some of the classical models, the Hegselmann and Krauss type models that yield polarized dynamics. We can reproduce those types of models, those types of outcomes really easily using these discourse sheaves by modifying the right-hand side of the dynamics a little bit. But we don't really have any new results as far as explaining why polarized states can be stable over time, things like that. That question in particular really requires more than just a mathematician's perspective. There's so much interesting sociology that's happening there. It really requires more than just a theorem to be able to say why it is we see the things we see now.
Okay, thank you. I have just another question. If there are no more questions, I will ask my question, which is like, you said, like, if we take a network of, in neuroscience, a neuronal network, is this model too simple for that?
So I don't usually say this out loud, but it's very much my hope that a modification of this model will wind up being useful in neuroscience. But at this time, I cannot report on any
that
specifics.
would be an interesting thing. Like, if you can change the H0, then you can improve, like, I don't know, communications.
Oh,
so
yes.
this is like very good for, this would be a big advance, no?
I agree.
Yeah. Okay. We have been spending like more than 20 minutes with questions. This was very interesting. Everyone is saying wonderful talk. It's fantastic. It has been a pleasure to have you here, even if virtually. If we were here together, now we will go with Aniceto, who is here, to drink these tapas, to drink this wine and have some tapas, even if we were not hungry. Aniceto, you want to add something? We cannot hear you. You have a problem with the microphone. You have the Mickey Mouse voice. So te ha puesto voz de Mickey Mouse. Okay. He's saying that he would like to come, I imagine, right?
I imagine so.
Okay, it would be great, but unfortunately, we cannot go for tapas now. We have to wait until we are all vaccinated and we can come and visit you, or you come here. We all meet in Barcelona next time and we go for tapas and we have this discussion. And also these interesting questions we got from people in Twitter who are, you know, in engineering and are interested in this. This was a very exciting talk and discussion. And I think you deserve a second round of applause. Let's give you an applause.
Thank you so much.
You hear me now properly?
And now we can hear you. You were like before.
Yeah, well, I'm just so sorry to be late. You know, in the